This is the last video about thermal actuation. The phenomenon we've not looked at is thermopneumatic actuators, in which we're going to use a phase change to create a pressure and use that pressure to create a motion. So typically this is going to be liquid gas or solid liquid phase change actuators. And how do they work? Well, basically you use a cavity in which you store either a liquid or a solid. Or in this case, we have stored a liquid here, and of course, part of the liquid evaporates always. There's an equilibrium here at T0 between the gas pressure and the amount of liquid. And when you're going to heat that system, part of the liquid is going to evaporate, and the pressure here is going to change. It's going to increase, and so you're going to be able to convert work via the movement of the diaphragm. Some ways of doing that is, for example, if you use a solid liquid, you can use paraffin and melt paraffin. Paraffin is like candle wax. It's a system that is maybe of all the phase change actuators the one that is most used, I would say. And if you want to learn more about it, I really suggest you to look into the publication of Professor Klaus Hjort in Uppsala University. They are working with paraffin actuators. So other ways is using water or using ice water system. You can also use going from a liquid to gas. That also gives you a good phase change. What's good with that is that this is a very strong actuation mechanism in the same magnitude as shape memory alloy. And you probably know that if you're from a Nordic country, you know that ice can break granite rock. So if you have a little crack in a rock and there's water running in there during summer, and then it freezes during winter and the ice expands, this phase change can crack the entire rock into pieces. So it's an extremely powerful actuator. The negative side of this actuator is that you need to incorporate a liquid or a gas and seal that in a microsystem. And there are simply no standard micro manufacturing methods or cost-efficient micro-manufacturing methods to do that. It's just very complex to pull little droplets of liquids and store them on a microsystem. So that is the challenge in that. Let's have an overview now on all the pros and cons of all thermal actuators. Yeah. So we have 4 types of actuators we're going to talk about: the thermal actuators, the piezoelectric actuators, the electrostatic actuators, and the magnetic ones. And you as an engineer will need to choose sometimes one of these principles, and then you have to know which should I choose. So it's very important to understand when should I take a thermal actuator and when should I not. So let's go through this. What's good with a thermal actuator? They exhibit a very high force, very high work output. Yeah? And you can also obtain large strokes. Thermomechanic actuators, so the ones that bimorph or monomorph materials, they're very easy to batch manufacture or to integrate. Bimorph is just 2 layers on top of each other. Monomorph is just one etching step, basically, to create that, to structure it. And they're also easy to actuate. I mean, they work by having heat. So basically, you just integrate a heater on the system, and which is very easy to build in a microsystem, a heater. And that means you'll be able to actuate the system. Another benefit is that if you do that, the actuator, so you build a resistor basically, and which you send current and that heats the material. That same resistor you can use to measure the temperature. So you can, for example, time multiplex, or perhaps even do it at the same time. You measure the resistance as you're heating. So at the same time, you can measure how much heat you add to the system, and you can use that as a feedback mechanism. What are the bad sides with thermal actuators? Well, high heat. Heating up a structure and cooling it down means it's going to take a lot of energy, and so these actuators will consume a lot of energy. Basically, the cooling, all the heat that you add to the system will be lost. Another negative point is that phase change actuators materials will be difficult for batch manufacturing, and that's both for shape memory alloys and for the integration of liquids or solids. Another point, which is really something you have to think of as an engineer, this system is inherently temperature sensitive. So if I want to, for example, integrate a small actuator in a car engine and in a diesel engine, my diesel engine has an operation temperature of, I don't know, 200-300 degrees Celsius. So that engine environment will make sure that my temperature is always, that my system will always be in the hot state. I will not be able to cool it. So thermal actuators can only work in environments where it's normally cool, and then you heat it to get something, to get a work output, but you'll be able to cool it. So you cannot use it in an environment where it's hot naturally. So I have to think about that. And another point that is often prohibitive is that the system is slow. And why is a thermal actuator slow? Well, it's not the heating itself. I mean, heating, it's just, you just pour in a lot of energy and it just will heat. And you can do that if you want to happen that fast. You'll just pour in a hell of a lot of energy and then you'll have a fast heating, no matter what the system is like. The problem is going to be in the cooling. Cooling of a thermal actuator will typically happen by leading away the heat through the structure to the surroundings, and you'll have convective cooling on the outside somewhere. And that process of getting rid of the heat, that takes a finite amount of time. So it's the cooling that typically will slow down the system. And you'll have typically, systems may work up to, if they're very well designed and not big and so on, maybe you have something like, maybe up to 100 hertz would be feasible as switching time, so 100 times per second, but that's going to be very difficult. Like the bigger valve systems, to open and close them, they'll typically take a half a second or even a second to just operate them, to go from one state to the other. Let me finalize the session with one quiz question. Thermal actuators convert heat into mechanical work. And I want you to think now about reversibility. Any of the systems, would it be possible to convert work back into heat? You think, 1, this is definitely never possible, or 2, yes, it will always be possible to convert work into heat using a thermal actuator, or 3, well, you say for some of the actuation principles it may be possible, but for others definitely not. Okay, so this is really, the answer is, of course, yes, it is always possible for all thermal actuators. And why is that? That has typically to do with entropy. It is always possible to transfer any motion. Motion is a low entropy kinetic energy into heat, which is a high entropy kinetic energy. So heat is nothing more than the unstructured movement of a lot of atoms in your material. And it will always be possible to, compressing something will always heat it up. And it will always be possible to heat. Basically, heat is the loss of any mechanism. And it's always possible to, any system is always lossy, and therefore it's always possible to convert work into heat.